Okay, so this will be a bit of a weird session. After very careful thought, meaning I ran out of time, I decided that what we really should do is just do like a totally unscripted, loaded data set and work with it session. Mainly because I ran out of time preparing, but we'll see how it goes. How many people have done data analysis in Python before? Okay, mostly. How many people have used Pandas? How many people would describe themselves as like, competent in Pandas? Okay, like half a person. Okay, all right, that's cool. So this will be more, it says advanced thing, but I think I already mentioned it's not really going to be, it'll be fairly introductory. Although we could do more advanced things. We'll load a data set and then we'll see how it goes. There is if you go to this website, which you'll see once this gets out of the way. So it's again under github.com/Neurohackweek. If you clone this repository, there is data, so you probably don't want to like download file by file, but if you haven't worked with GitHub, if you either use the GitHub client or ideally you have Git installed, just type git clone and then paste this from the command line, then you will get the full project thing, and then you can fire up the Jupyter Notebook. Is everyone comfortable with the Jupyter Notebook? Most people. I mean, there's no, as I'll show you, the notebook here is basically empty. I just left shells where we're gonna actually add code as we go along. So if you don't grab it now, that's fine. You can just follow along as we go, and then I'll upload once we're done with this session, I'll upload the current state of the notebook back to GitHub, and then you'll have a record of everything we did. So just to start, I figured we would use behavioral data rather than imaging data, just because we work with imaging data, every little thing will take, like 30 seconds to run. And the truth is, it doesn't really matter much. I mean, obviously, again, really, just you can, that's right. The look of disgust on your face. There are obviously some things that are specific to neuroimaging, many things, but the core tools typically are going to be fairly similar, and the kinds of operations we do will be similar. So I'm going to use a behavioral data set. Having said that, the data set I'm going to use is, can people at the back read that? Is going to be from the Human Connectome project. So we'll use HCP data to do this. And so hopefully, if you're not able to run this now and later, I'll just walk you through some of what we're doing. So these are all if you're familiar with Python, these are all the packages or modules we'll be using. We actually won't be using, I think, all of these. We'll see how it goes. We may add some as we go. So what we're going to do is we're going to basically figure out, how to work with a data set in Pandas, which is Python's sort of standard now. I would say it's sort of the R equivalent, right? R out of the box, you have this nice data frame thing that you can do all kinds of cool stuff with. And until like 4 or 5 years ago, Python didn't really have anything comparable. So you had NumPy, which was sort of for doing numerical computations very efficient, but it didn't really have like a nice data structure. NumPy has homogeneous arrays, all the columns have to be of the same type. Doesn't really have very good facilities for labeling axes. And so Pandas kind of fills that gap. It's sort of the data frame equivalent in Python, and gives us some other really cool stuff. So all you really need is to import Pandas, and by convention, the convention is to import Pandas as PD, just because it's easier to type. So what we're going to do here is read in a bunch of data, and that's all the code I have so far. Really, is just getting the data into one data frame, and then we'll start experimenting. And this is meant to be interactive, so you guys can say, hey, I want to see this, and how would you do that? And we'll try it out. So what we're going to do here in this data directory, I basically just dumped all the working memory e'prime outputs. How many people have worked with either run e'prime scripts or at least had the misfortune of dealing with other people's e'prime? Okay, so you know what these look like, right? They're not pretty. Like you have like 7 million columns. most of which you don't care at all about. They code things like, you might, but generally you probably won't care about like the offset between when the slide was supposed to appear and when it actually did because of refresh, the monitor, etc. So part of what we'll do is sort of figure out how to just discard or extract only the things we want from these kind of horrific data sets with just tons and tons of empty values. But so we have 200. I'm just using the first 100 subjects. As I mentioned, this is like fairly introductory. Despite what the title says, it's not advanced, so you guys can stay or go as you please. It's fine. So we have 100 subjects worth of data, 2 runs per person. This is the n-back task. Everyone familiar with the n-back task? Allegedly a working memory task. You can debate whether it's really a working memory task. It's definitely taps working memory among many other things. So that's what we're going to use here. And so the Python code I've written, this is the entire code that exists. We're just globbing for all of those files. So glob is just a nice utility that will let you search through the file structure and get all the files that meet this pattern. We're initializing a placeholder, a list for all the data frames we're going to extract. And then for each of those file names, we just read it in. Pandas has some pretty useful file reading utilities. Read CSV. It doesn't have to be a CSV. It's not in this case. We just specified that it's tab delimited. So we read each of those files in. And now one thing you'll notice about these files, if you look at them, is that they don't actually have subject IDs anywhere in there. In fact, does anyone recognize this software package? It's probably the only time you'll see Excel in this whole week. I actually think Excel is enormously valuable. This is the only thing it's enormously valuable for. It doesn't have to be Excel, right? But there is a time and place for firing up Excel, and it is this, to look at the structure of files really quickly. Any GUI will do this, but I like Excel for this one reason. No shame in using it to look at your data. There is shame in using it beyond that, though. Maybe a little. There's certainly things you can use it for. Okay, so we look at this data set, and here's what just one subject's run looks like. And again, as I mentioned, you notice some very funny things about this data, like tons of missing values, and some columns have the same value all the way down. And so these are things we're going to want to deal with. But here we're just reading each of these in, and we're extracting from the file name, because the file names, remember, have these things. You can see the subject number is embedded in the file name. 101309 is the HCP subject name. And so we're just going to pull that out with a regular expression, which if you were here like an hour ago, I talked a little bit about. And we're going to immediately store that in the subject column in the data frame, so just so we have that as well. And then we append it to the list, and then finally we concatenate this all with this concat operation Pandas provides. We specify the axis, so the idea is you're taking all these matrices and we're stacking them along the row axis. So we're just doing this. Right? We could also go columns, but that would be weird in this case because we don't want to have like 100 different columns all called subject. We want one column subject that specifies all the different IDs. And so if we execute this, it takes a few seconds. It's pretty fast. And now what we're going to do is just walk through various data analysis steps. And I've kind of broken these up into inspecting the data, preparing the data, a deeper look. But really, these first 2 steps are what consumes most of a data scientist's time. And it's really an iterative process. So typically, you don't like look at the data and then know, now I know all the steps I have to do in order to clean it, right? You do some stuff, then you look at it again, and you figure out if there are new problems, et cetera. And so I've just left, but for our purposes, we'll pretend that that's how it works, and we'll just start writing some code. And so, the first thing that you want to do with any new data set is like look at it and figure out what's going on and what's not right. So things we want to know are how big is the data set and what do the first few rows look like? How many of the columns contain meaningful information we actually care about? We might want to just discard some right off the bat so we don't have this giant file sitting, or this giant structure sitting in memory. How are values distributed? Are there missing values, et cetera, et cetera. Before we do that, let me say a little bit about Pandas a little more. So this thing we end up with after reading in the data, this data object here, is called the Pandas data frame. And if you just that's type data here, it will spit back out at you some text representation of that data frame. And it's just a table, really. Right? I mean, again, if you worked a lot in R or really any other sort of data analysis environment, you're used to looking at this. This is really it's the same thing as the Excel spreadsheet. I mean, it literally is just spitting that right back at you. The nice thing, of course, now is that internally what's represented for each of these columns are things like the type of the data, et cetera. And so we can now do all kinds of operations over that instead of just taking a look at it. So, for example, we want to know, well, how much data is there? And so by default, if you just print it this way, you can see that it'll tell you the dimensionality at the end. So there's 20,000 rows, almost, 126 columns. There's a lot of columns, there's a lot of garbage in there. We could also ask for the shape attribute on any data frame, which will tell you the same thing, contains the same information. Am I going too slow for people? Should I sort of, I mean, it's hard to gauge. Should I walk through like describing data, et cetera, or should we skip ahead? Yes, no, okay. And feel free to shout out, like, you know, what you want to, I mean, if you have ideas for things you'd want to look at. Otherwise, I'll just sort of walk sequentially through various steps. So we have all this data. We can ask, we can just take a look at the first few rows. Head is a nice command that will show you the first n rows. So, you know, that's the first 10 rows. There's also a tail. In this case, it doesn't matter because we just want to get a look at the tail. Will return the last, in this case, 10 rows. And that will give you a sense of what the data looks like. Again, lots of missing values. Okay. So that's just sort of a qualitative sense of what's going on. All right, but that's not super helpful. We know that there's some stuff in there we want to get rid of, but can we sort of more systematically get a sense of what has some value? So anyone have ideas for, like, how would we quickly get rid of columns that probably we don't need, or identify things that are not containing useful information? Thoughts, suggestions?
What about names?
Okay, yeah, nans. So right, so we can search for columns that have lots of missing values, and of course, if a column has all missing values, that's not a good sign. So Pandas has this nice apply functionality. If you call apply on a data frame, what that will do is apply whatever operation you give it on every column. Okay, and so we can very quickly apply some function on that. How do people know about lambda functions? If you were here in this room an hour and a half ago, you know about lambda functions. So lambda functions are just anonymous functions. They exist only within the scope of this call, and the only reason for that is convenience. So you could define a little method outside. You could say, you know, def count nans x, and then return the number of null values, but it's exactly equivalent to doing this in here, and so this just saves us some typing. Okay, so what am I doing here? I'm creating this method that will cease, the function that will cease to exist as soon as this is done, and is null just checks for every value in that series, in that column, whether the value is null or not. Then we sum over that because booleans can be implicitly treated as integers, right? 0, 1, and so this will give us the number of rows for each column that are set that have no value. So we do this, and you see something not very good, which is that a whole bunch of out of what, like 19,500 rows, a whole bunch of them have mostly missing values. And of course, there's some that have values throughout. Okay, so now why would that be? Well, if you have worked with E prime outputs before, and again, hopefully you haven't.
Could you slow down actually?
Sure. Yeah.
Go back up to the last command.
Yeah. Sure. Okay, so do you want me to walk through what the output is?
Well, just a chance to look at it.
Okay, sure. Okay, sure. So what this is returning is a series where every column, every row now is a column name, right? And so, and the value is the number of missing values in that column.
So by default, apply goes across columns rather than rows?
Correct, yes. But you can do, that's actually a good point to bring up. So do you guys know about this? So we're on the subject of IPython tips. So if you're inside a function signature, if you hit Shift Tab, it'll bring up the Python doc string. And so, I mean, this is super useful. Like a lot of times, like I forget what the arguments are, and so you hit Shift Tab, and you can also click this little thing, and that'll bring up the full doc string. And so when in doubt, you don't have to like go Google it. You can often just like remind yourself what arguments it takes. And so yeah, right here you see the axis, and so that second argument here, the first one is the function you want to apply, which is this lambda we just wrote. But we could have done this over rows, and so actually that's worth doing. Let's try this over rows. So 0 over columns. 0 will do it basically for every column. It'll take it'll apply the function over all the rows. We could apply it over columns, and see what happens now. And you can see that there's some missing values for almost every row, but there's probably no rows that are entirely missing, which would make sense in this context. So we can assign this to a variable. Let's call it nan counts, and then we can sort this. So the return, this nan counts thing is a Pandas series, which you can think of as a column, and it has a method called sort values, and that will just order things, right? So that just helps us see sort of very quickly. So now we have starting with 0 and running all the way down to the ones that have the most missing values. Sort values also takes an ascending argument, which is true by default, and so if you do this, it'll just invert it. And so very often you want to see like the top values, and so you can very quickly see the top values. Okay, so we flagged that now. We know that there are a whole bunch of columns that we don't care about probably. Why is this happening? Well, it's because the way this e'prime script was set up, it's dumping all the output into the same log file, and the script is set up to have different phases of the experiment. And so what's happening is you have like trial presentations, which are these rows, but then you also have like fixations and all kinds of other stuff, and they're just set up in such a way that the columns correspond to a particular part of the experiment. So fixations are fairly rare here, I guess, and so they don't show up very often. We probably, for the sake of, since we're just looking at behavioral data, we probably want to get rid of everything except actual trial presentations, so that have like reaction time, accuracy, etc. So one thing we're going to want to do is grab all the non-trial rows and just drop them right off the bat. Okay, let me just keep track of what we're doing. All right, what else could we do? What do you guys do when you load up a data set? This is meant to be, I don't have any, partly it's just, whatever package you use, we can walk through how you would do it in Pandas. Alternatively, I can just keep going. Yeah.
I don't seem to have the sort values method for the series object. Maybe I have an older version of Pandas?
Try sort. I think sort values it might be more recent. So then one thing about Pandas is actually fairly annoying. It's good and bad. It moves very quickly, and they're not afraid to break the API. So do not be surprised if sometimes you see code that won't run, and it's because you need the latest version, or some stuff has changed. Now that's good in the sense that it's that it improves rapidly, but it also is annoying because of many times when code will stop working. They're generally good about deprecation warnings. So usually they'll tell you hey, 2 versions from now this is going to stop working, but be aware that stuff will break. And as another reason why, as some of you heard, testing is really important, right? And if you don't know about testing, you should learn more. Okay, well so we have let's just clear this. Okay, so we have some ideas now about what kind of rows we want to get rid of. So let's clean up our data set a little bit. We don't have to actually delete stuff. We could, of course, just create a subset of the data set, but just for the sake of keeping things simple here, we'll start to just drop stuff. Now, one thing we've already talked about is the fact that we don't need all these rows, right? Not only are they not interesting, all these empty rows, but they could also do really weird things later on. We might try to group on certain values, and we'll have nan as a separate value show up in our summary tables, etc. So right off the bat, we can drop those. And so what we're going to do is we're going to pull out we're only going to keep the rows that have the value trials proc set in this column procedure block. And so we're going to index into our data set using a Boolean. So we're basically going to say only keep the rows where this statement I'm about to write is true. And so we can break this up into two actually to keep it simple. So we're going to first get the indices where this column is equal to this value. Okay, just comment that out for a moment, just to show you what that looks like, right? So it's just telling you false wherever this evaluates to false and true where it evaluates to true. And now we can index into the Pandas data frame with that Boolean. In other words, basically if we pass this in as an index, what we're saying is only keep the rows where that is true. And so we can do now this, right? And what will happen is that we're going to assign to data now only the rows that return true, and so these ones will drop out, these ones will stick around. And just to kind of make that point, let's print the shape before and after. Okay, so you see we just dropped 3,200 rows, and you can do this kind of filtering for any column at all. Obviously, you can and you can do conjunctions, disjunctions, etc. All the standard logic applies. Another way you could actually go about this is, how many people are familiar with the query interface in Pandas? Okay, it's actually super nice. Another way you could do this is an equivalent thing. Is you can type. So let me just say what we're doing here. We are keep only the rows that correspond to trials. Okay, so just to show you another kind of cool trick. It's actually kind of SQL-like. So if you've ever written SQL queries, I mean, they're not like super fun, but they're actually arguably better than writing really long things like this. So you can do things like, you can say, let's pick a different column. Okay, so this session selection list, I don't even know what this is, but let's say we want only the rows that have a value of 3 for this thing. So we can actually write this. We can say equals 3. And that's much nicer than writing this, this sort of thing, especially when the queries get long. So if we run this now, well, you can't see it because there's too many rows, but we can ask for the shape of this, and you can see that it only keeps 970 rows now. The query interface is also nice because you can very easily pass in variables. So let's say you define somewhere else, like maybe you're looping over some chunk of code, and each time you want to keep a different value of session selection list. So you could say SSL equals 3, and then you can do this. And that turns out to be very useful. There are many cases where you kind of are dynamically setting the value that you want to query on, and that's basically just a pointer that says, pick out all the rows where session selection list is equal to, this thing, and then it will take that value. So you can do very powerful and fairly minimalistic in terms of the amount of code you have to write using this. Does this make sense to people?
Is that at and then a variable?
Yeah, exactly. The at is basically a pointer that says you should find in the current scope the variable SSL.
Is that a general Python thing, or is it just a
No. This is just a query thing. This is just in the context of query. Yeah, and there are some restrictions on this. Like it will work. So query has some issues. Like we couldn't actually use query on this thing I just wrote because it can't handle the square brackets. You could obviously rename the column. It has some restrictions, but for the most part, I find query when you can use it, much more intuitive than doing this kind of logical indexing, especially when the query gets large. Because you can also, you can write things like this. So you can say, and I don't know what this feel free to rest start time thing is, but you get the idea. Oops, and so on. Okay. I actually think maybe I'll walk through indexing, because indexing is something that trips people up in Pandas. Are people comfortable with Pandas indexing? Loc and iloc and ix and Yes or no? Should I walk through that?
I've never touched it.
Okay. Okay. How do you? Well, okay. Okay. All right. Okay. So, have you worked on R?
Nope.
Okay.
But I've done lots of other stuff.
Okay. So like R is particularly nice, at least from like the user standpoint, because you can index like pretty arbitrarily with strings and integers or numeric values, right? So well integers at least. So you could do in R something like this, and that would be interpreted as give me the fourth row and the column, or the intersection of this column and the fourth row. Pandas will break if you do this, I think. We can try this, yeah. And there's actually a good implementation reason for it, which is that you can get into situations where it's quite ambiguous. Like you can have in Pandas rows that have the name for, and then what's it going to do? Do you want the fourth row? So Pandas, the Python philosophy compared to R is usually like, try to be a little more, it's funny because of course if you come from Java, Python seems like this like Wild West kind of environment, but relative to R, Python tries to enforce clarity, and so it doesn't want you to end up in a situation where like it could be ambiguous that you want the fourth row or the row named for. And so it forces you to index differently, and there's actually different kind of indexing mechanisms. If you just do something like this, so you just pass in, let's pick something a little more useful. Let me peek at my secret notebook with the answers, which is not on the GitHub repository yet. Okay, so let's say, well, I guess we can just take subject. So if we do this, what that will be interpreted as when there's only one index passed, Pandas will interpret that as a column. And so what you're getting here is all the values for that column subject. Okay. So I think that's R-like, and I think MATLAB does it the same way. But it doesn't really generalize, and so if you then try again, like as I showed you, right? So like in this case, well, let me back up. If you want to look at the columns and row indices, you can just look at columns and index. So columns is the names of the columns, and you can see those here. And rows also have names, and those are stored in index. And so you can see here the names. Why does this start at 5? Seems a rather odd thing. Right, so any ideas? Why does the index start from 5 in this case? Something we did.
We dropped.
Right. Yeah. So this is different from, these are not numbers, right? You think of these like intuitively as like the numeric indices, but they're not. What happened was when we read the thing into Pandas, Pandas said, oh, well, these rows don't have names, so I better name them based on their order of appearance. But when we drop that, it doesn't automatically reindex, which is actually a good thing because it has no way of knowing whether so it keeps the names, and that's why, again, you can't refer to these things the way you would intuitively want to, because it's going to create ambiguity. And so the name of the row now, the first row is 5. And the numerical index would actually be 0. It's the first row, but it has the label 5. Now, if you wanted to, and you probably would do in this case, if you wanted to reset it so that you don't have to keep this difference in your head, then you can do the following. You can say, in fact, we should probably add this up here. Let's say reset the row indices. So if you do this, then it will reset. It will basically renumber that index. And so now if you do the same thing, so if I show you the index now, in fact, it hasn't even assigned them, right? It's still a range. We don't need to get into details, but the idea is that it's not even applied. There's just like a rule for how you would actually generate these indices. But the first one is 0, the second one is 1, etc. And so that's good because we don't want to retain those original labels, right? We don't care about them. But we still have this problem. How do we pull out a particular row? Like if we want the third row only, how would we access that? And the ideal way to do this, the recommended ways to use this index are called iloc, which is integer location. So when you do something like this, iloc you are stipulating that you want the integer-based location, right? And it's unambiguous. So then Pandas knows that you want the sixth row in this case, I guess, because it's the index from 0, and not a row named 6 or 5. Now, that's one way to index. The other is loc, which is name-based, so location-based. And so if I do this, in this particular case, I get the exact same thing. But if we hadn't reset that index, those would give me two different answers, right? Loc would give me the row named 5, and iloc would give me the 5th row in whatever the data set currently is. And again, this is why you want to be clear, and why Pandas tries to enforce the usage of this. You can't force people to do it, but generally speaking, I recommend you get it's a little more typing, but it makes it very clear to the user too when reading the code, and they know whether you're indexing by position or by name. Now you can go in 2 dimensions here, so you can say, give me the 5th row and the 4th column, and then it's just like R. So you can think of this as if you've used R before, and that's giving you just that one cell, the cell that's at the integer index, row index 5 and column index 4. So 6th row, 5th column. Alternatively, you could have done something like and what is that saying? That's saying, give me the row that's named 6 and the column that's named subject. Okay. Is that clear? Now you can, of course, use ranges here. You can, or slices, I should say, just like in most environments. Okay, so that's saying, give me row names 6 through 10, still for the column subject, and so on. You can also, as I showed you, index into this with, you can use Boolean indexing, so you can pass a NumPy array or a Pandas series that has exactly the same number of values as the data set has rows, and then wherever it's true, it'll keep it, and wherever it's false, it'll drop it. And that becomes very useful when you're doing things like filtering, where you can just automatically sort of pipe the results of the filtering into the data set and keep only the rows you want.
So if you had dropped the row that was named 8, and then run that command, would it give you an error, or would it just give you all of the...
Well, I mean, let's try it. Easiest way, right, is try and see. So let's drop this reset index here. We'll have to reread the data, but that'll only take a couple of seconds. So we run that. We'll drop the nans again. And okay, and now we're going to call this, and it doesn't like that. Why doesn't it like that? Cannot get left slice bound for non-unique label 6. Right. I'm actually not sure why non-unique label. Well, we can look at the data, so let's look at it and see what's going on. I'm not sure. So it's a cryptic, it's a fairly cryptic error.
6, 7, 8, 9, 10.
But you can see, okay, so you can see what happens if you ask for it, right? So, and it could be, I don't think Loc should be trying to detect ambiguity. Maybe that's what it's doing. It realizes that there's that issue. I mean, unambiguously, if you ask for the 6th to 10th row, then it will find them. But you can see that those now have the wrong, I mean, those are the original indexes. And again, this seems very counterintuitive, but I have run into many situations using Pandas all the time where it actually saves you from indexing into the wrong thing. And if you get into the habit of doing this, then there's never any ambiguity. And it's always clear, both to yourself later in reading the code, and also to anyone else using it, that this is what you mean to do. But it is a little more typing, and I remember being frustrated when I first moved from R. I was like, why do I have to type like iloc, and there's also ix. So ix, if you really want to be flexible, you can do something like the following. Well, so here there's ambiguity, so it won't let you do it. But this ix is sort of the equivalent of native R indexing, where it'll try to guess what you want, but they even in documentation recommend you not use it because it can cause problems. And you think it's such a simple thing, right? Like, just give me the 4th row, and it turns out like there's all this like complexity. Okay, so all right, so let's reset the index here. Okay, so all right, so that's fine. So we've thrown away all those rows. What else might we want to do? Well, a lot of those rows, it looks like, don't have very much information in the sense that they have the same value, it looks like, going all the way down. And that might be just because the way the prime script is set up, right? It's just logging something that might vary at the level of subject. It might never vary. The experiment might have the exact same value. Like laptop refresh rate probably is not changing, at least for a session. And these things are just noise. So how do we identify the rows that we want, or the columns that we want to select and get rid of? As a general, I should also mention, I think I've already said this, like, I'm only showing you how to do this so so you're aware of the various filtering operations. typically you don't really need to worry about like what should I drop. You just pull out the stuff you want, create a new data set, and move on. There's no reason in general to like worry about like the original object not containing all the stuff that is exactly what we wanted. So what we can do is again use apply. Any ideas? How do we identify all the rows that contain no information? There's various ways you can do this. Ideas? Well, so one thing we could do is, again, we could write a little lambda. We pass in each column, and then we just ask, so Pandas has this nice n unique, which tells you the number of unique values. And we don't want two x's there. And if you run that, it's going to tell you how many unique values every column has. And you'll notice if a column has like one, like this across the entire data set, right? So like it cannot be useful to us if it has exactly one value. If we really want to know, we should assign it to some variable and keep that around, but this is not going to be useful for data analysis. And so we can sort on all these things. And so just like we did before, we could now say remove all columns, or let's say keep only columns with more than one unique value. And again, I'm sort of, you could do this all in one line, but just to keep things clear, we're first storing all the indices that, well, actually we can even do better than this. We can say, give us all the values, all the rows where there's more than one unique value, and then again we can now, or sorry, all the columns, and we can again just index. And that doesn't work because things rarely do. Let's see what this looks like. Okay. All right. Backup plan is we get, so we're just going to store those unique counts, and now we're going to make our indices, and I'll explain this in a second. Okay, so what am I doing here? We're storing all the unique counts, so every column, the number of unique values, and then we're saying give us only or basically give us the rows that have more than one unique value, and we're taking the index, which is the column name, and those are now going to be our indices for the next step. And so then we can, so if you print this, these are now column names. And so now we can say data equals data. Just to be explicit, the colon means everything, right? So remember, rows, columns, loc is by name, so we're saying give us all the rows that match these named columns, and the names are coming from here. I know this can seem like a little like magic when you're first seeing it, but when you work through it and understand logic, then it'll be much easier to generalize to other similar kinds of operations. And so if you do that, now we have, look at the shape, and we should have, okay, now we're down to 69 columns and still 16,000 rows. And so now we're at the point where we might start to think about like doing something else with the data. We've got to the point where like most of those columns probably contain some information, and we can start to think about actually looking at the data itself. And we're almost out of time. Okay, so let's say you've got. Sure. Sure. Yeah. And if you have questions, feel free to ask. And the rest of the week, by the way, like just flag me down at any point and say, hey, could you like help me play with my Pandas data set? I'm happy to help. Okay. Any questions or no? Okay.
Just wait, it's a little hard for me from here to tell to get everything specific.
Yeah, and again, I mean, the intent is not necessarily that everyone follow along with these particular examples, and I will upload this later on, so you can.
Well, yeah, if you're gonna upload it later.
Yeah, everything. I mean, I'll upload whatever we end up with and clean it up a little bit as well. Okay, so all right, so we have something that we sort of feel, reasonable. Again, like you wouldn't in practice do this, but just to give you a sense of the kind of operations that you will do to filter the data set, select out columns, etc. All right, let me just paste in a little bit here, and then I'll kind of walk you through what's going on. Okay, so just to skip ahead, right? Really, as I mentioned, we don't probably need most of this stuff. So we would ideally just like load up Excel, look at the columns that we think are actually useful to us. And then because they're given weird names like stimulus and block, we might want to come up with more sensible ones. Different ways you can do this in Pandas, but simplest one is probably just to replace the columns. So first what we're going to do is select out only the columns we want. These ones we think are important. We'll call them old cols. And then we're just going to replace the names with new cols, which are just easier to type and keep track of. And so this is just indexing again. So bad habits. I should be doing this, right? What I had would work, but this is really probably the clearest way to make clear what's going on. Is we're indexing by name and keeping only the old columns, and then you can set the column names directly like this. And now if we do this, we should only have 8 columns. 16,000 rows, that makes sense because, well, I can tell you this, there's 100 subjects, and I think, 160 rows, 160 trials per subject. Okay. What time does the next one start, Ariel?
Next one is in 15 minutes.
Okay, cool. All right. Okay, now we can actually start to look at the data. And so one thing we can do is, yeah, go ahead.
Did we actually get rid of the names at some point?
Do what?
Did we getting rid of the names?
Yes. Although, I mean, you don't have to. I mean, there's a lot leading up to some grand demonstration. So if you don't, nothing bad will happen. But I ran this here. So first we just counted. Where'd it go? Oh, did we? Oh, sorry. We didn't. There actually aren't any nans in what we're left with. So what we did is here. This is an effect. So we got rid of all the rows that aren't trial rows. Right. So that's all. We did 2 things. First of all, we got rid of all of these rows here that don't have these kinds of values, target type. And so that drops a lot of the nans. And then these disappear because remember now I just selected out only 8 columns to keep. And so implicitly we've gotten rid of all this other stuff. But you're right that we didn't. Pandas has a really nice way of doing that. So if you ever are in a situation where you're like, I know that any row that has at least 1 nan somewhere is bad, then there's a very simple way to handle that. You can just call drop NA. And that will magically make all rows and all columns. No, I take it back. Only all rows by default, although you can specify the axis. Either all rows or all columns disappear. You want to be careful with this because, if any row or any column is missing a value, it'll drop that. What you can do, however, is you can use the subset argument, and so you can tell it, well, only drop the row if these columns are missing. So you can say, well, I only care about the NAs in columns run, subject, trial type, and then magically all the rows that have NAs in one of these, but not in other ones, would disappear. A lot of the Pandas philosophy is to kind of, you have sort of wide functions in the sense that a lot of functions have just tons and tons of arguments. And it can be frustrating because it takes a while to learn the API well. But once you do, you find you can do things really powerfully because like this, for example, you don't have to sort of figure out, well, how do I select out only the rows that I want to apply or care about the nans? You can usually do this with, you can also have thresholds. So you can first binarize values and then only the values above that will get kept, right? So you can do all kinds of interesting things if you look at the doc strings. And it's worth reading the Pandas documentation because it's I wouldn't say it's the greatest documentation in the world. It's certainly not, but it is at least explicit about most of the things you might want to use. Let me just make a note. Okay. All right, so one nice thing about Pandas in more recent versions, they've implemented some basic plotting functionality into Pandas itself. It used to be that in the early days you kind of had to pass that along to matplotlib yourself, but now you can actually inspect data really quickly. And so, for example, we can say, we have reaction time, which we've just renamed, right? So we pulled out this stim RT column, we called it now RT, and we can do something as simple as, actually I'm not sure off the top of my head what this will do. I think it'll give us a histogram. Oh, it's just treating it as it's a line plot. So this is not useful, but what you can do is plot takes an argument called kind, where you specify what the kind of plot is. And you can see right there, by default, it's line, but we're going to say we want a histogram, and then we can pass it other arguments. So we can say we want 100 bins. I wouldn't recommend using Pandas plotting functionality for like actual plots you care about, but it's really nice because you can very quickly explore the data without having to load up something else. So what we're plotting here is ignoring subjects or whatever, just plotting all the reaction times. It's a distribution of all reaction times from all subjects. Anyone see a problem? All right, so if you were going to analyze this, what is like one like glaring problem with this distribution of reaction times? What's that?
0.
Yeah, right. There's this giant spike at 0. Why might that be? Any guesses? Like, why would you have a response time of 0? No response. Right? Subject didn't respond. No response. We probably don't want to code that as a 0. Right? That has a different meaning. Someone responding 0 is not like going from 0 milliseconds to 100 is qualitatively different than going from 600 to 700. And there's probably not many analyses where we would want to treat this as if it's as a ratio variable. Okay, so just by plotting that, we've learned something about our data. And so we can handle this in different ways. For present purposes, I'm just going to do what we did a moment ago. We can say, let's say that we're going to set all the rows where again, let's be explicit about this. We can say, first let's identify all the rows where the reaction time value is exactly 0. And now we will set those values to np.nan, which is nan. There's other ways you could do this as well. I guess we don't really need the, I'll just put this down here. Okay. And now if we were to replot this, let's do this in the cell below. Hopefully what should happen is that's gone, and it is, right? Because the plotting functionality will ignore nans. It doesn't know what to do with them, so they're gone. And so so we've corrected for that. Now, again, you might not want to do that. How you handle that's up to you, but the point is looking at your data very quickly in one line of Pandas code, and then we can fix that also in one line. And so now we've solved that problem. What else might we want to do? What do you guys normally do when looking at data? Or otherwise, it doesn't have to be plotting. So we can do some magical things using a library called Seaborn, which I'll talk about in the visualization session a little bit. I think I probably already imported it. So Seaborn has some nice tools for very quickly visualizing large amounts of data. Let's see if this works. Does not work. Let's actually come back to that. Okay. Here's an example of now delving a little bit more into what's actually going on in the data. So now we're sort of moving away from very basic data cleaning stuff towards like actually scientifically meaningful observations. No stats yet. Stats is like what you do way down the road once you think you actually understand the data. So Seaborn has, and I'll talk about this more, has this nice gridding capability. It basically lets you create what are called data-aware grids. And so the idea here is you create a facet grid, which is just sort of like a placeholder that says we are going to map some aspect of the data onto the dimensions of this grid. And what we're saying here is we're passing in that Pandas data frame, and we're saying, look, we want the columns of this grid to reflect levels of n-back type. So n-back type codes for 0 back and 2 back. There's 2 levels. And so we're basically just saying setup. You can think of it as now a grid where every column now is going to get its own level of n-back type, and there are only 2 in our case. Hue or color will code for stim type. So that's, there's 4 stimulus types in this task, body, face, I forget the other 2. And so that sets up this grid without having actually told it what to do yet. It's just setting up a grid that knows that whatever we want to do, it's going to apply it to every n-back type in columns and different colors for different stim types. And now we can map any of the plotting capabilities of Seaborn, and I'm not going to show them here, but I will at 5 o'clock, and there's the documentation for this is incredible, so you can go and take a look. What we're saying now is we want to map we've already constructed this data aware grid. We want to map this plotting function, KDE plot, which plots kernel density estimates, for the variable reaction time. And that's what you're seeing here. So really, I mean, this is kind of, I think, cool, right? That like, and you can do this, in various other languages and with tools, but it's kind of cool that in like 2 lines of code, we've gone from the data set to breaking things up really nicely, so that you can already see a little bit of what's going on in the data. And so, so what do we learn from this? Well, you want to be careful because these are density estimates. They're not like amplitudes here. You get the reaction times, but you can see right off the bat that like 0 back reaction times are much smaller, which makes sense. The 2 back is more difficult. You see there's about 200 millisecond difference between the sort of the peak of all these guys and the peak here. There's also much less variance, so these ones tend to cluster more closely, which if you know anything about 0 back makes sense. 0 back is a task where you're just trying to detect a particular image. Here you actually have to think about whether the image matches something, and there's different trial types, and so there's going to be more variance. You can also see that there seems to be some difference between the stimulus types, which is not necessarily something intended when the task was designed. I don't know which is which here, but one of these 4 stimulus types seems to be consistently slower for both conditions. Now, whether that's sort of meaningful in an inferential sense, you would have to discover with some statistical tests, but that seems, given the data we have, pretty reasonable. Remember, this is, again, this is just for illustration. This is all not ignoring subjects. So these are not like, these are like just modeling all the reaction times, not the way you would want to do it in your analysis. You would probably want to do this over subject averaged values, right? Does that make sense? And in fact, actually, that's a good segue to how you would do that. And this is one of the most powerful things you can do with Pandas. Very clean and simple grouping operations, by which I mean you can take that data set that contains data for all subjects, all runs, et cetera, and apply the same operation to different chunks of it, let's say subjects. And so you can, let's say I want the means for all subjects, I want the mean reaction time for every subject broken up separately by n-back condition and stimulus type. Very easy thing to do here. Pandas has this group by method that will create groups. So we say submeans equals data.groupby, and now you specify what columns define the groups. And so the unique combination of all the columns you give it will define one group. And so if we say subject n-back type, well, let's just do that for now. What it's going to do is will give us a row for every subject, every n-back type. There's 2 n-back types, so we'll get, and 100 subjects, so we'll get 200 rows here, right? And if you just do this, nothing really will happen. And the reason is because this is just creating groups. We haven't asked it to do anything. Those groups are just sitting there. And now we can apply operations on top of this. So if we just say that, now we have a sort of a group by object that's sitting there waiting to be told what to do. And we can do all kinds of things really easily. Like, for example, we can say, this gets a little counterintuitive, but it's super powerful. So we can say, take the column reaction time. And the reason it's counterintuitive is because remember, this is not like it's not a single array or data frame. It's actually a whole bunch of, it's like, you can think of it now as 200 separate data sets. But it's going to pull that column out for every one of these data sets. And there's some built-in functions like mean that will automatically be applied to every group. And so if we just do this, what we get is something like this, right? And so a very simple, clean way of going from this gigantic data set to aggregating over the combination of subject and back. So subject for every subject you have 0 back, and the mean of the reaction time. But it gets better. You can actually do things like, so mean in this case is a built-in shortcut for aggregate or ag. You can either do aggregate or ag for short. And so you could have done, will this work? I think it might. Let's see. But you can actually pass in lists. So if we do this, Pandas is clever enough to realize, oh, I get what you want. You want me to apply for every column that we're keeping in these groups, each of these operations. And so just like that, we've now got a data set that contains the means, the counts, the number of rows, the standard deviation, and the means for reaction time broken down by that n-back type and subject, right? And so it makes it very quickly to it makes it very easy to very quickly drill down to exactly the data you want. You could also pass in multiple columns here. So we could have said we want both reaction time and response accuracy. And now it's building what are called multi-indexes. So it's, and those get really complicated. I would suggest you try to stay away from them if you can. Almost everyone I talk to who uses Panda regularly is like, yeah, just no, multi-index, bad, you're gonna have a bad time, pretty much guaranteed. It's very powerful, but it takes a while to wrap your head around it. I don't think I've wrapped my head around it fully yet. But nonetheless, if you know what you're doing, you can get out something like this, and again, very quick way to summarize. And of course, you don't have to just apply these built-in functions. You could have created your own. So you can say, if you're so inclined, I don't know why you do this, but you can say add 1, and then you return, well, let's say you take the mean and add 1. And now you could add that right here to this list. And I think this will work. Yeah. Okay, so you just wrote your own little powerful function that can be applied over arbitrary groups of that data, and it will respect the fact that you had multiple columns. It will create the thing for each one. Completely nonsensical, of course, but you could substitute anything you want in this function. Performance is something to keep in mind. The built-in methods are super optimized. Obviously, if you start writing your own 50-line chunk of code, and this is being applied, in this case, to 200 groups, it may get slow, but on the other hand, you're writing very little code. So it's a question of whether you want to optimize your time or the CPU time. And one nice thing about Pandas, for things that are built in, it's often actually faster than either native Python or NumPy, because it's been heavily optimized for this particular use case. So that's a nice kind of thing. And of course, now if we save these, let's call them subject means, then we can go off and do other things with this. Okay, so now we have these means, and now we can try to do something like this. This would not really be appropriate to apply on this particular data set, but just to give you some other things you can do in Pandas very quickly. You can apply this core method over any data frame, and what it'll do is it'll take it'll just give you the pairwise correlation between every pair of columns for every numeric variable. So if it detects strings, it'll just ignore them, but here it's giving you the correlation between every pair of columns in that data set. Let's see what else we have here. I think we're actually running over. Ariel, who's up next?
Jeremy.
Oh, okay. Okay. So hopefully you get a sense of a little bit of the stuff you can do in Pandas. And again, I'm happy to do as many sit down people or do as many of these kinds of things as people want the rest of the week. And there's plenty more I haven't showed you. It's an incredibly powerful package. And learning it really well, if you're working in Python, I'm not necessarily going to say that it's superior to the R solutions. I think these environments are pretty much comparable at this point. You can do pretty much the same stuff in either one. But if you are working in Python, it's really worth your while to get to know Pandas really well, because you can save a lot of time and actually compute much more efficiently if you're familiar with some of these things than trying to run your own loops, etc. So I'll stop there, and I'm happy to pick up some other time, and I'll hand it over to Jeremy.